Welcome to this video on acidity and the pH scale. The big question here is, what does the pH of a solution tell you? And I'll give you the answer straight away. I'm going to contrast this to Ka and pKa, which we've covered in previous videos, which tell you the tendency for a particular molecule to act as an acid. So they are the properties of a molecule. The pH, in fact, is slightly different. It's not to do with the actual substance. So a strong acid won't necessarily have a particular pH value. The pH tells you about the acidity or indeed the alkalinity of a solution. So let's relate this to where you've come from in terms of pH. So probably when you first started off, you were taught about acidic solutions, which might contain something like lemon juice, and then you've got alkaline solutions, which might have contained something like soap, and in the middle was neutral. So that was your first indication of acids and alkalis. And then you probably got taught about the pH scale, which ran perhaps from 0 all the way up to 14. It was usually associated with particular colours of indicators, such as universal indicator, shown here. And then a little bit later on, you probably, perhaps in your GCSE studies, began to relate the pH scale to the concentration of hydrogen ions, H+, or H3O+, the hydronium ion, as you now know. And a neutral solution had an equal concentration of H+ and OH-, whereas an acidic solution had more H+ ions than OH-, whereas an alkaline solution still had some H+ ions, but there was a higher concentration of OH-. So, how does that actually allow us to calculate what the pH is? What is the relationship between the pH, these numbers, and these values? It's not just a one-to-one correspondence. This isn't 1 mole per decimeter cubed of H+ ions necessarily. So let's think a little bit about that. And this was the work of Soren Sorensen, a Danish chemist, around about 1909, where he noticed that the pH, the H+ concentration, much like the acid dissociation constant, had a huge range of values, and so he decided to use this logarithmic scale. So pH, it roughly means something like the power of hydrogen, sometimes the potential of hydrogen, but I think power of hydrogen is a helpful way of understanding it, the power of hydrogen. So what Sorensen basically said was that he was going to relate the H+ concentration to 10 to the power the pH, like this. And so with this kind of logarithmic description, it allowed him to compress a huge variety of H+ concentrations to a scale that just ran from 0 to 14. And this was what he said. So the H+ concentration is 10 to the power minus the pH. So, for example, if we happen to have a pH of 1, and this formula is telling us that the hydrogen ion concentration is 10 to the power minus that value of 1. Now a negative logarithm here is going to be, a negative power is the same as 1 over a positive power, so this is just 1 over 10 to the power 1, or 1 over 10 moles per decimeter cubed. So this is a tenth of a mole per decimeter cubed. Now if we go to pH 2, change to pH 2, the hydrogen ion concentration now is 10 to the power minus 2, which if we stick that into our rules of indices, we're going to find that's 1 over 100 moles per decimeter cubed. And that gives us a really, really useful relationship, which is, we can see here a 1 unit change in pH. So the pH increases 1 unit. And that results in a drop in concentration of a tenfold, a decrease by tenfold in the hydrogen ion concentration. And that's the case all the way up the pH scale. So this increase here is a decrease of 10 times the H+ concentration. And that would be the same going all the way up. And in reverse, if I drop by 1 pH unit, that would be an increase of 10 times in the hydrogen ion concentration. Now, final thing is just to try and think about reversing this formula. So suppose you want to know what is the pH at a particular hydrogen ion concentration. How are you going to do that? Well, we need to somehow reverse this formula. So we need to understand what is the inverse operation of 10 to the power something. And the answer is it's a logarithm. And in fact, in this case, the base of the logarithm is the base 10. So we're going to take logarithms of both sides of this formula. Logarithm to base 10 of the H plus concentration. And we're going to take a logarithm with base 10 of 10 to the power minus, so I'll just remove the square bracket to avoid the confusion, 10 to the power minus pH. Now if you never heard of logarithms before, I'll show you in a second that it's just a button press on your calculator. You can think of them as just the reverse operation of raising to a power. So we'll carry on going with log 10 of the H plus concentration there, and if we apply that to this side, these guys will cancel each other, so you get minus pH over there. And this is more commonly written in the following way. pH is minus the logarithm of base 10 of the H plus concentration. Now that is a crucial formula that you need to know. So this relationship here, really, really important relationship. In fact, both of these relationships you're going to have to commit to memory. So let's see how these can be used in some examples. So I've got the two key formulae up here. What is the pH of a solution when the H plus ion concentration is this? Well, we're going to just stick these numbers in our formula, and I'll just show you how we're going to do that. So this is pH minus log base 10 of, in this case, 0.02 to get our value. Now how we're going to achieve this operation, as I said, it's just a button press on a calculator. If you've got one of these ClassWiz type calculators, you just click that button, you'll have to tell it you want base 10, and then you just input the value you want afterwards. And if you've got one of this type of calculator, log by default is a base 10 logarithm. So when we do that, we find that we get a value that comes out like this, 1.698 897, and so on and so forth. And the question is, well, how many significant figures should we give our answer to? Well, if we look here, we've actually got two significant figures. These two are the significant figures. So this is two sig figs. And so we need a two sig fig answer. So you might think, right, good, that's 1.7. Actually turns out to be incorrect. The correct answer would be to write 1.70. So this is actually two significant figures, and in fact it's most common to give pH to two decimal places, which corresponds to two significant figures. Now why is that? Well, significant figures in pH values are a little bit different, and in fact the only significant figures are these two after the decimal place. So significant figures in pH value, only the figures after the decimal point are significant. Now why is that the case? I just want you to consider these two numbers, normal numbers here, 330. Now I don't have to tell you that these two numbers are different numbers. They are one significant figure numbers. Here are the significant figures. They're 1 SF. But they're different numbers. And perhaps it's easiest to note this. The reason they're different is because these are, the 3 here happens to be in the hundreds column, and the 3 here happens to be in the 10 column. Or if we write them in standard form, we can see this is the significant figure, but then in addition, we also need the power of 10. This number here, this is the power of 10. So in order to make a number, you need to know the significant figures and the power of 10. Or the place value, you might say. Now when we get a pH value, 1.69897, and so on and so forth, then because this is a logarithmic scale, this number at the front here is actually telling us, I'll just put the decimal place back, this number here is actually telling us the power of 10. We get the first number before the decimal place, be that 1 or 13, it would tell us the power of 10. The significant figures start after the decimal place. So these numbers are the sig figs. So we always give pH value to 2 dP, which corresponds to 2 significant figures. If you happen to have a 3 sig fig concentration, you would give 3 sig figs, which would be 3 decimal places. But usually pH meters only tend to measure pH to about 2 dP, so this tends to be the most common.